Hey everyone, my name's Luke. So I'm a final year PhD student at University College London, and I'm going to be talking to you today about a model I've been developing over sort of the last year of my PhD called the diffusion piecewise exponential model. And this model, or really a prior structure for Bayesian inference, is a model for extrapolating survival curves and extrapolating hazard functions when we have sort of administratively censored survival data. So I'm going to introduce the model and kind of motivate this a bit and then finish off my talk by introducing the implementation, as it were. Just before I begin, this is a joint work with my PhD supervisors, Sam Livingston and John Lucabai as well. Okay, so extrapolating hazard functions. This is a problem we're probably all fairly familiar with, but I'll motivate it anyway. I run my clinical trial and I run it. I have budget to run it for maybe this is just under 3 years. And I observe data in this observation period. Fantastic. But I get to the end of my trial and I'm faced with this problem. It's a good thing or a bad thing, depending on your perspective, where a large number of my patients are still alive and haven't experienced the event I'm interested in. So this is great news for patients. But as a statistician, as a health economist, this is slightly harder news because if I'm trying to characterize my hazard function over a sort of lifetime time horizon, this becomes very difficult. And particularly for us, this problem's quite tricky because rather than trying to estimate a treatment effect or some other sort of estimate, which is we can purely infer from this observed period, we're trying to characterize expected survival or mean survival, which is going to go as a benefit into our economic model. And this is going to be influenced by both of these periods. So it's going to be influenced by my observation period, absolutely, but it's also going to be influenced by what happens in this extrapolation period. And essentially, as I observe more data, as I observe more events in the extrapolation period, then my inferences for expected survival are going to be increasingly influenced by what I infer in this extrapolation period, which is basically by design, because I don't have any data there, is inherently going to be driven by prior assumptions of some form. So what does good extrapolation look like? Some criteria for principled extrapolation. I've got these criteria here. These are quite influenced by some recent work by Chris Jackson, but there's also this fantastic review, sort of nice decision support unit review on flexible survival modeling as well. So in the observation period, we'd like flexible models where my inference is going to be driven by the data. So I wouldn't like to rely on parametric forms. I'd like to basically let the data speak for itself as much as possible. And there's lots of very nice recent examples of this. I've got these references at the end of the slides. Yes, so there's been lots of work in this area very recently. We'd also like that any prior information or any assumptions I place on this are only weakly informative in this period. That again, I'm getting this idea that the data are speaking for themselves. Then in the extrapolation period, well, this is inherently going to be driven by prior assumptions. And whatever I do, whatever, Bayesian frequentist paradigm I work in, whether I have external data, whether I don't, this is unavoidable. I'm always going to be driven by these prior assumptions and I can't get around this. What I would like, however, is any assumptions I place on my model to be explicit. And also, so they're interrogable. So if I then put this model to a regulator, they can interrogate these assumptions and say, are these assumptions reasonable or not? And a more subtle point is I'd like the constraints on these assumptions to be as minimal as possible. Essentially, I would like my prior assumptions to inform the model rather than the model informing my prior assumptions. And we'd like to design a model that can do this. So my starting point today is going to be the piecewise exponential model. So I've got this piecewise constant hazard function like so. I'm talking about log hazards today. And a very standard approach, if you wanted to extrapolate with this model, would be to place some prior dependency on my log hazards. So you could, for example, the very, very typical one is to use this random walk behavior. And then you can place some knots as well. And if you place these knots into your extrapolation period, then your uncertainty with this random walk prior is going to increase. But this isn't fantastic for a couple of reasons. So firstly, my extrapolations are going to be very sensitive to this choice of knot location. So if I place several knots down in a very short period in my extrapolation period, my uncertainty is going to blow up very quickly. Or conversely, if I place very few knots, my uncertainty is going to blow up very slowly, but this is going to be purely dictated by you as a statistician. Secondly, we can probably do better than this random walk prior, right? This is just saying my uncertainty is going to keep increasing forever. And we know this isn't true. We have more prior, even in the sort of very, cases where we have very little prior information. We know this is not true. We know we could do better than this. So that's what I'm going to try to do today. So this is where I call term the diffusion piecewise exponential model comes in. This is made up of two parts. So I maintain this piecewise constant log hazard function that I've kept before. And the very first part is so I've got these knots. So these are the breaks in my hazards. And I'm going to say these arise from a Poisson point process prior. So I'm going to say these come with some intensity gamma and some on some intervals. So this is just my observed period interval. I'm going to say my knots arise from this case. And this means we're going to be able to learn the number of knots I need in my observation period, like so. And the idea of this, why this helps with extrapolation, is because once I've learned this, fitting the model to my observed data, is once I then want to extrapolate my hazard function into my extrapolation period, I can then use the posterior I can learn the intensity I get from this prior, either from setting this gamma parameter based on some predictive criteria or by placing a hyperprior on it. So I can learn this, and then this gives me a way of extrapolating my knots into this extrapolation period. And intuitively, what's happening is if I get a very volatile hazard in my observation period, I should get my uncertainty in the extrapolation period should very quickly blow up, or I should very quickly have my prior assumptions take over. Conversely, if I observe a very stable hazard function in my observed period, then I should have a very stable hazard function in my extrapolation period. So we're trying to learn something about the extrapolation period from my observation period. This still doesn't get us around the random walk behavior. And so the second part of this is I'm going to say, well, I'm going to assume that my log hazards here are discretizations arising from some diffusion like this, or a stochastic differential equation. So I'm not going to get too much into the form of this, but what this essentially means is I can use this drift function here to specify prior information about my hazard function in the long term. So for example, in a very basic case, I could set this to 0 and I just recover my random walk behavior. So remembering we're modeling on the log scale and converting back to the natural scale, this just gives me a random walk for my hazard, like so. But I might have some idea about a range of values for my hazard function in the long term, and I can encode this as a stationary distribution like so. So this is this middle plot. So we're starting with some hazard initial sort of distribution for my hazards here, and then we're interpolating between this and some stationary distribution for my hazard in the long term, like so. I also might have some information about my hazard, for example, saying I don't know the value it's going to take. I just know it's going to keep increasing in the long term, and I can encode this as well, like so, on this plot on the right here. So this allows me to take any existing prior knowledge I have about my what my hazard function should look in the long term, and encode this in a principal Bayesian manner into my model for the observation period and the extrapolation period. Oh, sorry. Okay. So this is what the model looks like on some applied data. So this is just a data set on colon cancer patients. This is a fairly kaleidoscopic plot, I'm sorry, but essentially each line here is a different prior assumption for what my long-term hazard should look like. So I've got these different ones. So we've got a couple of stationary distributions. I've got this one I've called Gompertz dynamics, which is just increasing dynamics. And then this random walk behavior, which is our sort of standard base case. The first thing to note, so on the left here, we've just got what happens in the observation period. And in this case, I get this flexible hazard. But the really important thing here is that essentially my prior assumptions aren't influencing what I observe in this observation period. I'm letting the data speak for itself, and my assumptions about what happens in the long term aren't affecting my inferences to the observation period. But then when I look at my extrapolations in the long term, what we see is that we get very different results depending on the assumptions I've encoded. So where I get this random walk behavior, I've got these two stationary distributions, or these increasing dynamics, which are going to vary quite a lot depending on the sort of prior I've elicited from my experts, like so. Okay. I'm getting slightly short on time, so this is just a very small point saying we can do non-proportional hazards very easily. I maybe won't go into too much detail because I'd like to get onto the implementation. So As I said, but I'm working in the Bayesian paradigm, and the current state of the art in this case is to use stan, probably called via rstan, like so. We can't do this in our case, and the primary reason for this is this prior on the space of knots. So stan can't handle discrete parameters, it can't handle posteriors where the dimension of your state space changes as you sample, and so we can't use stan. Instead, we developed a Markov chain Monte Carlo scheme based on a new class of processes called piecewise deterministic Markov processes. This would be a talk in itself if I was to introduce these, so there's a reference, but I'm not going to go into the details today. These are great, they're very computationally efficient, and they require almost no user tuning, even for sort of very challenging Bayesian model averaging problems. There's very new methodology, and we require bespoke implementation. So this is available, and there's a Julia implementation available at the package here, diffusion piecewise exponential. But this isn't great for this workshop, and makes me feel like I've just signed up for the wrong place because, of course, this is R for HTA, not Julia for HTA. And please don't worry, I'm not suggesting we, split the workshop. I'm not proposing a breakaway workshop. We are going to keep this within R, I promise. So let's do a very high-level comparison of the two languages. I kind of have two parts to my research. I have myself as a more applied statistician working in HTA, and I have myself as a computational statistician. As an applied statistician, I love R. It's got this fantastic statistical modeling ecosystem, and especially for HTA, it's got lots of fantastic packages, driven by this workshop. You compare that to Julia, and this is, there's some statistical modeling, but it's not fantastic, and there's just no HTA ecosystem there. Okay, so we don't want to be doing applied work in Julia. But if I want to write as a computational statistician, Julia is fantastic. You get fast code native in Julia that's comparable to C++. It's very easy to develop in, and it's got a great ecosystem for computational statistics. And you compare this to R, where it's very hard to write very high performance code, and your speed relies really on C++, which I find quite scary. I appreciate the next talk is telling me why C++ shouldn't be quite scary, so I'm looking forward to this, but for me, it's quite scary. Okay. So what's the idea? The idea is we're going to try and compute in Julia, and we're going to use this lovely computational language for my computation. Then we're going to convert this into R, and we're going to be able to use R for all my analysis. And I'm going to give, in my final few minutes, just a very brief overview of how we do this. So I'm very sorry, these slides are very boring and black and white. I tried to make them better, but I couldn't. So I'm just going to simulate some data here. This is all in Julia for the moment. I just simulate some data and I specify my MCMC settings. We're not going to worry too much about this for the moment. The main thing I want to focus on here is how I specify my prior assumptions, like so. And this just goes into the object here called basic prior. In Julia, this is what is called a struct, but for purposes of thinking of this as R, this is very close to a list. It's kind of a list with a specific purpose. And there's two really important points to this. Firstly, my Poisson process prior. So what I'm doing here is specifying a Poisson process prior just with intensity 7 on my observation interval. And then my underlying diffusion. So I'm choosing a Gaussian stationary distribution in this case, with mean centered log 0.29 and standard deviation 0.4, like so. Then what I can do is just run my MCMC chains, like so. Okay, so this is a Julia implementation, but you can do this all in R as well. And the primary thing here is just using this Julia call package, like so. This allows us, for example, to generate and format my data in R, like I've done here. You can then take these objects in R and assign them in Julia, like so, using this Julia assign function. I've hidden some of this stuff here in this setup file, but then you can use this Julia command function to directly run some Julia code, like so. But very importantly, you can then return the model output in R using this Julia eval function. And this core idea here is that this just should fit naturally within any existing modeling flows. So I can say I've formatted my data in R. I do all my pre-processing in R. I go to Julia just for the computation, and then I return my output to R for all my analysis after this. So we can do just the really computational part, the bit that Julia does really well, and use R for its strengths too, like so. Okay. These are some very brief references of what we talked about today. If you don't like them, I have others. And I think I'm at time, so I'm just going to leave this slide up here. But just to say, yes, this package is available now. If you go to if you follow this link or go to the GitHub, it has the code examples I've included. And we also have this preprint out as well, which, yes, so feel free to go and read that. And I'm very happy to take questions.
Right, so thanks a lot, Luke. So we have 4 minutes and there's 3 questions already. So Doan is saying, can you encode priors which allow for turns in the hazard function in the extrapolated portion, and can this be implemented as a relative survival model?
So yes, so for the first part, yes, you can incorporate priors which allow for these turns. Essentially, the way you do this, so I talked about having the stationary just distribution. And actually, if I just go back a second, you'll notice how I formatted this. I have this essentially as a function here, which is saying t goes to this log 0.29. Essentially, this is specifying a function as the mean, and this can depend on this time t. And so you could add a time varying mean function to the stationary distribution. So the way I have this in mind is, for example, if you have a reference population and you'd like your long-term hazard function to behave like the hazard function for this reference population, you can incorporate this specifically into this stationary distribution, for example. We have examples of this in the paper as well if you're interested. And so, yes, if this had turns in the future, you could absolutely incorporate this. For the second part, so this is saying, can I incorporate this into a relative survival model? Um, yes, yes, you can. I have it. I mean, like, uh, you can't in our current implementation, but like theoretically, yes, you can, and it's something I'd like to include. Currently, you could include this as a prior, similarly to how you'd encode that where you do this time varying diffusion, and you'd allow essentially allows your hazard to converge towards this hazard in the long term. And again, if you wanted to incorporate something where this is a proportional assumption in the long term, you can do these kind of things as well.
Right. Howard is saying we've got nothing against Julia, so that's good news for her. And calling and making links between her and other packages. The question is, can your new MCMC simulator processes be used for other applications like network meta-analysis?
Um, So the again, so on a very high level, yes, piecewise deterministic. So MCMC based on piecewise deterministic microprocessors is just another MCMC scheme. It's just an alternative to Hamiltonian Monte Carlo or Gibbs sampling. The settings piecewise deterministic microprocessors work really well in are case. Sorry, I'm just going to go back to the discussion. So that's up. Um, there's so the setting we have where you have this kind of transdimensional sampling. So that works really well. They can essentially do this without evaluating any additional likelihoods, which is really nice. They also work ways where you have where you have lots of independent modules which only need to interact at certain times. You might think of this as having some sort of product structure in your posterior. Um, and they also work really well in big data settings. So they have this really nice property, which you can't do with Hamiltonian Monte Carlo, for example, where you can subsample the data at each iteration of your MCMC scheme, and this preserves your posterior. So if you just do this with standard MCMC, this means you're not going to get you're biasing your posterior, you're not getting the inferences you want. You can do this in an unbiased manner for these processes. So I think there's lots of potential for these processes to be used for some of the really challenging applications that we see in our field. And yes, if there's anything in mind, I'd be really happy to continue discussing this because they're very cool, but there's not been very much applied work done using these processes.